Unseen places, built to defy nature, until nature fights back. The Leaning Tower of Pisa weighs thousands of tons on a foundation 3 meters deep. Across 30 structures, hidden weaknesses reveal why no repair remains final. The decisive forces act where the visible structure ends, in soft ground, cracked rock, exposed steel, and moving water. I keep returning to the bargain every builder makes with terrain. A tower can be stabilized, a cliff can be cut, a gorge can be crossed. But each answer leaves a new surface for frost, wind, sediment, or salt to test. Loads shift, joints loosen, slopes drain and swell. In this video, we examine how extraordinary structures hold their ground and why nature keeps changing the terms. A tower weighing thousands of tons depends on a foundation only about 3 meters deep. Pisa's 57-meter bell tower rests on compressible sand, clay and silt, and its top once stood more than 5 meters from vertical. Uneven settlement appeared while the lower levels were still rising. The stonework did not simply lean. Later builders adjusted the upper stories, leaving a slight curve in the tower. Long pauses in construction helped by accident. They gave the soft layers time to compress before more weight arrived. By the late 20th century, the displacement had become too serious to ignore, and the monument closed in 1990. The task was not to straighten it completely, but to stop the movement without erasing its identity. Engineers secured the structure, stacked temporary lead counterweights, and removed small amounts of soil beneath the higher side. That controlled subtraction reduced the inclination while preserving the lean. The tower reopened in 2001, but the intervention did not end the contest. Instruments still track movement, groundwater, and seasonal shifts in the soil. I see Pisa less as a monument rescued once than as a structure kept upright by repeated inspection and correction. Its deepest opponent is not wind or stone, but unstable earth carrying every ton above it. A royal capital rose onto a sheer rock, where height strengthened defense and strained daily life. Roughly 180 meters above Sri Lanka's central plains, King Kashyapa I built a fortified capital here in the 5th century. Below the summit, moats, reservoirs, and water gardens formed more than decoration. Channels, pools, underground conduits, and pressure-fed fountains turned water control into a display of authority. Above, cisterns and storage cut into rock helped sustain life through dry periods. Without that reserve, the summit's defensive advantage became a liability. Food, building materials, and water had to climb without modern lifting equipment. Steep ground that blocked approach also tightened every supply line. The route enforced control. Rock gardens, narrow stairways, exposed galleries and gateways compressed the ascent before the final passage between the monumental lion's brick paws. The mirror wall and fresco gallery made that climb ceremonial as well as defensive, revealing images and views before the palace precinct. What strikes me is how authority depended on maintenance below its grandest rooms. A blocked conduit, a depleted cistern, or a damaged stair could weaken life at the top. At the summit, royal power ultimately narrowed to a practical count: how much water remained, and whether the route from the plain still worked. Only one castle facade faces open air. Behind the rooms, the mountain becomes the building. Prejama fills a cave mouth beneath a limestone wall over 120 meters high, with 14 kilometers of passages behind its rooms. Only the outward facade is fully exposed. Behind it, natural rock forms walls, ceilings, chambers, and an irregular base that the masonry must follow. An earthquake damaged the medieval castle in 1511. Much of the present Renaissance structure came from the rebuilding that followed. The cave provided storage and a route through the mountain, later tied to legends of Erasmus of Lueg receiving supplies while the castle was cut off. Depth improved protection, but opened more paths for water. Karst water seeps through fractures. Humidity affects timber and interiors, so drainage must keep runoff away from occupied rooms. Heavy rain and freeze-thaw can loosen cliffstone. Cave voids and irregular rock also deny the castle the simple foundation of level ground. Maintenance must track several fronts at once: masonry, cave, drainage, and limestone. A repair that ignores one can shift pressure into another. I cannot call Prejama secure on architecture alone. Its safety is still set by rainfall, freezing weather, and movement in the fractured rock. The fortress's strongest defense is not a wall at all. A road climbs about 160 meters up exposed limestone and passes through 14 separate gates before reaching the summit. Recorded in the early medieval period, Hokosterwitz was heavily strengthened by the Kievenhüller family during the 16th century. As pressure grew along the Ottoman frontier, they turned the ascent itself into the main defense. Tight bends stop large groups from gathering speed. Narrow passages, walls, and guarded positions then force every climb into a different shape. That is what I respect most here. The ground converts every step into work. The gates do not stand apart from the rock. They exploit its steepness. Every defensive bend and gate also slowed the people hauling provisions upward. The route that protected the summit made supplying it harder. If access closed, cisterns and protected storage became essential. The summit offered control of the plain, but it demanded preparation for isolation. Weather tests that bargain without pause. Water works into masonry joints, winter freezing widens cracks, and vegetation takes hold where stone must remain clear. So the fortress survives through drainage, masonry repair, vegetation control, and repeated maintenance. One blocked drain or widening winter crack can turn the defensive height back against the fortress. An ordinary trip to school once required handmade bamboo ladders fixed to a cliff. At Atelier, more than 2,500 steel steps replaced the ladders in 2016, but the mountain remained too steep for vehicles. The Yi village stood high above a valley in Sichuan's Daliangshan Mountains. The ladders were not an adventure route. They were the link to schools, markets, medical care, and roads below. Children often moved with adults. Food, tools, and cargo rode on people's backs, consuming strength before the return climb began. Rain made bamboo and rock slippery. Fatigue and loose footing then reduced an already narrow margin for error. Steel brought firmer steps and handholds, but it did not shorten the climb or carry vehicles to the settlement. That distinction matters to me. The steel stair gave residents firmer footing on the cliff, not a way around it. Later, many residents moved closer to the county center, while the old settlement and route drew tourism. That left a harder choice: improve access to the ancestral village, or move daily life away from the obstacle. Neither response makes the mountain passive. Steel secured each step, yet the cliff still decides how much effort separates a home from a school, a market, or medical care. A road cut to end isolation is still governed by the rock around it. Completed in 1977, the Guoliang Tunnel runs for more than a kilometer through the Taihang Cliff, with narrow sections and abrupt outer openings. Before it opened, Guoliang depended on a steep stair route to the valley. Food, tools, building material, and residents needing medical care all faced that bottleneck. In 1972, a small group of villagers began cutting into the red-brown cliff with hand tools and drills. 5 years later, a road passed through the mountain. The irregular openings were working ports. They carried broken rock out while bringing light and air into the excavation. Changing width and rough spacing exposed the manual construction, section by section. The tunnel solved isolation, but it also created work that never ends. I respect that resolve, but rock still sets the operating rules. Runoff must be controlled, loose rock inspected, and traffic managed through blind curves. Rain and fog cut visibility. Winter ice reduces grip, rockfall interrupts movement, and tourism vehicles add pressure where the passage narrows. The villagers finished the excavation in 5 years. Keeping the road open is the work without an end date. A cliff of soft sandstone carries an archive that rain can slowly erase. Nearly 200 caves and more than 7,000 Buddhist sculptures occupy the near-vertical face of Maijishan, some dating back to the late 4th century. This was never simple carving. Many figures were modeled in clay over wooden or stone supports, leaving fragile surfaces dependent on the climate inside each chamber. Outside, narrow stairs, platforms, and walkways bind the cave mouths together high above the valley. They carry the same burden once faced by carvers and worshippers. Every movement, tool, and repair must cross exposed rock. The mountain keeps changing. Earthquakes have separated sections of the cliff, while wind, rain, cracking and falling stone continue to work on the softer sandstone. Water is the quieter pressure. Shifts in humidity can weaken clay and painted surfaces without producing an obvious failure outside. Preservation, therefore, reaches beyond the sculptures. Crews must stabilize rock, control drainage, monitor cave air, and maintain access structures without burying the historic facade under new construction. The archive survives at the speed of conservation. One crack, one cave climate, and one fragile painted surface at a time. A sanctuary built for isolation now depends on crews controlling the mountain above it. About 1,200 meters above sea level, Sumila occupies narrow ledges on a wet rock wall over the Altindere Valley. The complex grew around a natural cave used as its central church. Churches, chapels, cells, kitchens, storerooms, and guest spaces were stacked wherever the cliff allowed a foothold. Much of what remains expanded under the empire of Trebizond. Steep passages linked the buildings, while an aqueduct and storage rooms made long isolation practical by securing water and supplies. But the same Black Sea climate that feeds the dense forest keeps pressing water into masonry and painted interiors. Moisture does not need a dramatic opening. A small fracture is enough. In cold weather, water in those fractures freezes and expands. Stone loosens above roofs, paths, and entrances, turning the cliff itself into a maintenance problem. Modern conservation has required loose rock removal, barriers, stabilization, and periods of closure. The work is not separate from the monastery's history. It is what allows occupation and access to continue. I find Sumela powerful in that constraint. Every roof rests beneath a wet mountainside, and its beauty lasts because stone and water are managed again and again. Monasteries more than 300 meters above the cliff base still depend on ropes and cables for ordinary supplies. At Meteora, 24 monasteries once occupied isolated rock pillars. 6 remain active and accessible after more than 6 centuries. The pillars are sandstone and conglomerate, shaped by erosion above the Thessalian plain. Their narrow summits offered withdrawal and protection, but almost no spare ground. Hermits first used caves and ledges. From the 14th century onward, organized communities raised walls, chapels, cisterns, roofs, and courtyards where every load had to move vertically. Before permanent stairs and bridges, monks, pilgrims, food, timber, and building material rose in rope nets, baskets, and hoists. Removable ladders controlled entry, yet they also made every repair an exposed operation. Roads and carved steps changed access, not the foundation. Walls and balconies still crowd limited summit space, while rain enters joints and wind reaches every facade. Cold cycles add another pressure as trapped water freezes and loosens material around paths and anchor points. Crews cannot treat the rock as a finished base because the base keeps weathering. Old rope nets and present cable hoists reveal the same limit. Life on each pillar is only as secure as its next supply line and rock inspection. The limestone ceiling above Esher is both shelter and threat. At Esher, a narrow shelf holds the inn, while the ground drops sharply toward the Alpstein Valley. There is no service road and no ordinary loading bay. Visitors reach Ebenalp by cable car, pass through the Wildkirchli caves, then walk another 15 to 20 minutes. The caves carry evidence of prehistoric use and later religious retreat. That longer human history does not change the present constraint. Every useful load must still cross steep, restricted ground. Food, fuel, water, maintenance gear, and waste cannot move by truck. Each season depends on disciplined handling between the cableway and the inn. The overhang blocks some precipitation, yet it creates another duty. Runoff and loose material above the rear wall must be watched, because shelter and exposure come from the same rock. Snow, ice, storms, and trail conditions decide when the inn can operate safely. A calendar matters less than whether the mountain still permits reliable access. This is not engineering that levels the site and expands without restraint. The building stays useful by keeping its footprint, deliveries, and maintenance subordinate to the ledge. Each reopening is conditional. The trail, snow, runoff, and rock must all grant another season. Around 80 people can shelter on a ridge that offers almost no horizontal ground. Above 3,300 meters, Caban de Bertol rises through 4 levels, with open space falling away on most sides. The final approach does not end at a broad terrace. It ends on steep steel ladders, anchored directly into the rock. Those rungs are not a dramatic flourish. They close the last gap between a high alpine route and shelter used during long ski mountaineering crossings. At this altitude, thin air magnifies fatigue before the climb is finished. Storms can erase tracks, while ice can turn each exposed rung into a fresh test. Inside, every necessity is packed upward. Food, fuel, bedding, and emergency equipment for around 80 people must fit within a footprint. The ridge refuses to widen. Water relies heavily on captured or melted snow. Major supplies and maintenance materials may need helicopter support, so even basic comfort carries a long chain of work. The route itself will not hold still. Retreating glaciers and changing snow cover can alter the approach, forcing climbers to plan against new ground. Before each arrival, changing ice and snow may redraw the final approach. The refuge offers shelter, not certainty. Monte Rosa Hut can meet most of its energy demand locally, yet its water and approach still depend on changing ice and snow. Nearly 3,000 meters above sea level, Monte Rosa Hut operates beyond roads, utility lines, and a municipal water supply. The current faceted building opened in 2009 through a collaboration involving the Swiss Alpine Club and ETH Zurich. Its components were prefabricated in the valley, then flown up by helicopter. Assembly had to fit the short alpine construction season. At this elevation, efficiency begins before the first wall rises, because every load must cross the mountain. The aluminum exterior reduces weather exposure. A dark, south-facing band gathers solar energy, while deep insulation, controlled ventilation, and heat recovery hold onto warmth. Together, those measures let the hut cover most of its energy demand locally. But local power does not make the building independent of the landscape. Liquid water is not continuously available, so meltwater must be collected and stored. Wastewater is treated on site before discharge, turning isolation into a daily engineering duty. Glacier retreat and unstable seasonal snow are changing the walking approach. The hut can manage heat, power, water, and waste, but it cannot command the ice and snow outside. A mountain can gain cable cars and barriers without gaining a single meter of level ground. On Mount Huashan, South Peak rises more than 2,100 meters above granite ridges and deep ravines. For centuries, pilgrims and Taoist practitioners moved through Huashan Gorge toward temples and hermitages, fitted onto the few ledges the mountain allowed. Their route never flattened the slope. Cut steps made patches of granite usable, iron chains supplied support where no broad path could exist. Cable cars reach the north and west peaks, but exposed links still bind the summit network together. Old stairs absorb crowds at narrow junctions. Rain strips friction from stone. Winter ice hardens that problem. Strong wind presses across the ridges, and fatigue makes each uneven rise less forgiving. Access, therefore, depends on work that rarely draws notice. Clearing drainage, checking barriers, examining chains, and finding wear or corrosion before movement becomes unsafe. The famous plank walk is only an optional, harnessed section. The larger engineering achievement is the route around it, kept usable across near vertical granite. Every repaired chain is an admission written in iron. Gravity has granted a route, not surrendered the mountain. The main structure on this fortress pinnacle is not a wall, but a staircase cut into the mountain itself. Kalavantin Durg stands as a steep basalt spur beside Prabalgad in Maharashtra's western Ghats, with its upper route reduced to irregular footholds. The approach runs from Thakurwadi through Prabalmachi. Distance is not decisive. The ground narrows and steepens until the pinnacle controls movement. Few fortress structures remain. The lasting intervention is the stairway, cut into rock and shaped by basalt rather than a standard plan. Near the top, broad landings and continuous railings disappear. Each weathered step offers limited footing, so hands often become a second point of balance. Monsoon rain changes every contact surface. Wet basalt, mud, fog, and sudden storms cut traction and visibility just where the route allows least correction. Water follows the stair cuts, accelerating erosion and leaving debris. Access carved into the mountain can help weather loosen it. The dry season reverses the pressure, not the difficulty. Heat, scarce shade, and dehydration replace slippery stone, forcing a rhythm of effort. The decisive skill is not courage, but restraint. Wet basalt, heat, and limited footing must set the pace. Missing slabs once exposed the metal skeleton of a hydroelectric walkway, barely a meter wide and about 100 meters above the river. El Caminito del Rey crosses Gaitanes Gorge, where the original concrete slabs rested on metal supports fixed directly into the rock. Built in the early 20th century, it linked two hydroelectric installations across terrain split by the gorge. This was industrial access, not leisure. The path depended on concrete slabs, metal supports, bolts, and the cliff holding together. Water and falling rock tested every connection. Corrosion and neglected repair left missing slabs and exposed beams. Once safe operation became impossible, authorities closed it in 2001. A reconstructed boardwalk opened in 2015, fixed higher on the same wall. The old structure remains below, exposing the cost of deferred maintenance. The new route does not erase exposure. Helmets, controlled entry, one-way movement, inspections, and weather closures matter as much as timber and steel. Wind can halt access. Anchors, decking, barriers, and the cliff demand repeated checks. Safety is an operating discipline, not a finished object. The abandoned slabs below the new deck make the warning visible. Safety disappears when inspection and repair do. Only 65 centimeters of steel grating separates hikers from open air. The Charles Cornin suspension bridge runs nearly half a kilometer and hangs roughly 85 meters above the Grabengufer ravine. Its first lesson came from the slope itself. An earlier crossing had to close after rockfall made its position unsafe. Engineers did not try to command every loose stone. They shifted the new line higher, steering the crossing beyond the most active debris zone. From there, the load runs into main cables, then into massive anchors buried in both mountain sides. Stabilizing cables and damping measures restrain the deck when wind and footsteps begin to move it. The steel grating also yields less surface to the wind, but it leaves the ravine visible beneath every step, so the structure reduces pressure without hiding the exposure. Construction had little room for machinery and only a short mountain season. The terrain controlled the method as firmly as the design. Wind, snow, lightning, rockfall, cable tension, and seasonal conditions still drive inspections, maintenance, and closures. Its safest decision was a retreat. Move above the rockfall zone, then keep watching cables, anchors, and slope. "11 meters of platform project beyond the limestone at Ravnavlashka, about 1,200 meters above sea level, with no columns beneath the outer curve." Its horseshoe shape looks simple, but the outer edge hangs on a cantilever. Steel and reinforced concrete beams pull every load back toward anchors and foundations set inside the bedrock. Visitors add weight and movement. The mountain adds stronger demands. Bora winds, temperature swings, snow, ice, and water working into cracks in the limestone. That last force matters because karst is fractured ground. Drainage must carry water away before weather can widen weaknesses around the foundations. The glass floor and transparent rails do not disguise the drop toward the Adriatic. They make exposure part of the structure's purpose, while the real resistance stays buried in rock. Even access carries a limit. The narrow mountain road restricts traffic and emergency movement, so safe operation begins long before anyone steps onto the platform. Visitor numbers, weather, glass panels, joints, drainage, anchors, and the surrounding slope all require control. A clear floor is only the visible surface of a much larger maintenance burden. The glass is the spectacle. The real structure lies behind it, where anchors, drainage, and inspections make fractured karst dependable. The edge of this walkway has no glass wall and no guardrail. Its barrier moves with each participant. The Macau Tower skywalk circles the tower about 230 meters above the ground on a track roughly 2 meters wide. That moving barrier is a full-body harness, a safety line, and an overhead rail. Together they keep a continuous connection around the outside of the tower. Responsibility shifts to the track, connectors, harnesses, repeated checks, and trained guides. The protection normally supplied by a fixed wall. Guides inspect fit and spacing before each circuit. Safety is reset participant by participant. Weather can halt the skywalk while the tower itself remains open. Wind limits and lightning procedures therefore become structural boundaries, even though neither can be seen. Macau's coastal air brings humidity and salt onto exposed metal. Add thunderstorms and typhoon winds, and corrosion checks become part of the architecture, not a task hidden behind it. The tower is built to tolerate movement in wind. Outside the glazing, movement and height are harder to ignore, so staff, inspections, and operating thresholds carry as much weight as concrete. The skywalk does not pretend the drop is absent. It faces height directly, held by restraint hardware, kept reliable through disciplined inspection. For more than 700 meters, a deck barely wider than 1 meter replaces the descent between Slamnik and Klum, 95 meters above the valley floor. Opened in 2022, it replaces a long descent and climb with a narrow moving crossing. The price is hundreds of meters of steel exposed to mountain weather. Main cables pull the deck toward towers and huge anchors buried in both slopes. Those anchors depend on rock and ground that must carry every shifting force. Wind never presses evenly. It changes direction and load across the span, while stabilizing elements restrain motion before it exceeds operating limits. Winter adds snow and ice. Temperature swings alter cable length and tension, turning an apparently fixed crossing into a structure that is always adjusting. Visitors add another moving load. Numbers and weather must be controlled, and monitoring can trigger closure when conditions move beyond safe limits. The bargain is severe. Less effort on the ground demands more discipline in the air. Inspection and maintenance are part of the bridge, not support work. It joins the slopes only while cables, anchors, and operators respect wind and open space. Glass turns the void into the view, but the structure must control every force that exposure amplifies. At Zhangjiajie, the deck crosses roughly 430 meters of canyon, almost 300 meters above the valley floor. The bridge is about 6 meters wide, but width does not remove exposure. Multi-layer laminated glass panels sit inside a steel structure, carrying the load while leaving the gorge visible below. Cables carry the span toward anchors fixed into steep sandstone cliffs. Each connection must absorb changing wind, temperature, and crowd movement without letting motion build across the deck. Nature tests different parts in different ways. Wind works across the full span. Heat and cold shift materials. Footsteps and impacts concentrate force on individual panels. Glass therefore demands more than strength. Crews check for impact damage and lost clarity, replace separate units when needed, and inspect the joints and cables beneath them. Early popularity exposed another limit. Structural capacity and crowd control are not the same problem. Timed entry, visitor caps, inspections, and temporary closures keep human load from becoming uncontrolled. The gorge becomes an attraction only when panels, anchors, joints, and human loads are measured. The canyon remains a 300-meter measure of engineering limits, answered by inspection, restraint, and repair. A skyscraper-scale elevator is fastened directly to a mountain cliff. The Bai Long elevator rises more than 300 meters along a quartz sandstone escarpment in Wulingyuan, linking the valley floor to the plateau above. 3 double-decker elevator systems make the ascent. Their lower run passes through a shaft inside the rock. Above it, steelwork and glass cars stand exposed beside the cliff. Rock shields part of the machinery, then becomes the foundation and anchor for steel-facing open mountain weather. The lift replaces a long climb with a rapid vertical transfer, but speed demands control. Excavation, foundations, power, brakes, and cliff connections must work together under heavy daily visitor flows. Wind pushes the exposed frame. Lightning, rock movement, and interrupted power require operating rules, backup measures, and a clear way to bring people out when normal travel stops. Access also changes pressure on the landscape. Some walking routes carry less traffic, while large groups gather at the upper stations and pressure concentrates around a few access points. Maintenance is therefore part of the ascent. Crews inspect rails, cables, doors, brakes, and cliff attachments because one easy ride depends on many parts holding their alignment. Bai Long overcomes the climb, not the escarpment. The cliff stays severe, testing joints where steel, power, and rock meet. A major expressway crosses empty air where the mountains offer almost nowhere to build. The Beipanjiang Bridge carries that road about 565 meters above the river, across a cable-stayed main span of roughly 720 meters. Towers and anchor foundations had to grip opposite slopes before deck sections could advance outward, with no support beneath the growing span. Poor access made deliveries of steel, concrete, cranes, and workers another operation shaped by the mountain. Then the wind entered the schedule. High above the canyon, gusts complicated lifting and alignment, while temperature differences made the completed deck move. Cables carry traffic but permit movement. Expansion joints absorb temperature changes instead of resisting them. Opened in 2016, its 1,300-meter length was then the world's highest bridge by deck height. It removed a major descent, turning the divide between Guizhou and Yunnan into a direct expressway crossing. But completion did not settle the argument. Cables, pavement, drainage, joints, foundations, and nearby slopes still demand inspection because wind, rain, heat, and rock keep changing the loads. At expressway scale, the old bargain remains. The road saves hours only because cables, joints, foundations, and slopes are never treated as finished. A railway curve crosses 6 stone arches, then disappears directly into solid cliff. Landwasser spans about 136 meters, rises roughly 65 above the river, and meets a tunnel with almost no room for correction. Built in the early 20th century, the viaduct forced railway geometry into a narrow alpine valley of river, slope, and rock. The track climbs and curves at once. Large conventional scaffolding would have obstructed the water and been difficult to support, so temporary lifting towers raised material as the masonry piers grew. Local stone supplied mass for repeated train loads, but mass alone was never enough. Every wheel passes vibration into the arches. Each winter lets water freeze and thaw inside vulnerable joints. Vegetation finds gaps, drainage can clog, and track geometry can shift. More than a century later, the graceful line depends on unglamorous work, checking stone, renewing mortar joints, clearing water, and correcting rails. That maintenance protects more than masonry. It preserves the exact handoff from exposed curve to tunnel where accumulated error has nowhere to go. Landwasser proves that railway elegance rests on endurance. Stone, mortar, drainage, and rails maintained, while water, frost, and traffic test every arch. A routine train becomes a structural test the moment it leaves the mountainside. Mala Rijeka carries the Belgrade Bar Railway nearly 500 meters, with its track about 200 meters above the valley floor. Completed in 1973, it used 5 concrete piers. The tallest rises more than 130 meters from its foundation. Those dimensions were not chosen for spectacle. The railway had to connect the interior Balkans with the Adriatic port of Bar, while mountain terrain left few acceptable gradients or curves. Construction pushed deep foundations into steep lower slopes, then lifted material vertically as each slender pier climbed into stronger wind. Alignment had to remain exact across a void where access itself consumed time and effort. Operation repeats the test. Each train concentrates weight through rails and deck, down narrow supports, and into ground that must keep holding. Crosswinds press sideways. Temperature changes lengthen and shorten the deck. Water challenges drainage, and seismic movement can alter forces at the foundations. Inspection is difficult because the components most exposed to weather are also suspended far above the valley. Mallory Heka turns an ordinary train into the valley's recurring load test. Every passage asks whether concrete, foundations, and maintenance have adjusted quickly enough. Beyond the mountains, the adversary becomes salt water. Qinghai Bay can be crossed in minutes, but corrosion begins on day 1. Across Qinghai Bay and Dalian, more than 6 kilometers of roadway rest on dozens of piers standing in salt water. The bridge uses different structural forms because shallow marine sections, navigation space, and shoreline connections demand different spans and foundations. The result looks continuous, but the forces below it keep changing. Waves and currents can scour sediment from around the foundations. The threat develops underwater, beyond any inspection made from the deck. Salt attacks higher up. Spray and humid air expose the steel, while chloride can penetrate ordinary concrete and corrode the reinforcing bars inside. Protection therefore comes in layers. Coatings, dense low permeability concrete, sealed details, and drainage that gives seawater nowhere to collect. Expansion joints and bearings absorb movement as temperatures shift. Inspection must reach what the deck cannot reveal: marine growth, foundation condition, expansion joints, bearings, and components carrying repeated wind and vehicle loads. Construction ends above the water. The longer work continues below sight as foundation surveys, coatings, seals, and drainage are renewed before corrosion becomes failure. A sea crossing more than 50 kilometers long keeps major shipping lanes open by making the road disappear beneath the seabed. Between 2 artificial islands, an immersed tunnel nearly 7 kilometers long carries road traffic below, while major vessels continue above. The Hong Kong-Zhuhai-Macau route links 3 urban centers, yet no single structural form could satisfy the estuary. Tunnel elements were prefabricated, floated into position, lowered into a prepared trench, joined underwater, and covered with backfill. Alignment had to hold in deep, moving water. That tunnel removed a conflict from the surface. Tall bridge towers near busy navigation and airport approaches would have created additional hazards. Elsewhere, long viaducts cross deep water and soft marine deposits. Their foundations, bearings, joints, and artificial islands must accommodate traffic, tides, wind, and seabed settlement. Salt keeps working into exposed materials, while typhoons load the crossing and vessel traffic narrows the margin for disruption. Below, tunnel seals and drainage guard a road that cannot tolerate seawater. This complexity is not excess. It is the price of occupying a changing estuary. The sea forced the route to become bridge, island, and tunnel, and it still dictates the work required to keep all three connected. A lighthouse occupies almost every usable meter of a rock, where even routine repair must wait for calmer water. Tourlitis rises on a narrow pillar offshore from Andros, with no road, no harbor, and no broad platform for a maintenance crew. The original lighthouse began operating in the late 19th century, marking a difficult coastal approach in an island region shaped by shipping. Its cylindrical tower takes nearly the whole summit. The staircase is cut and built around the rock because the site offers almost no level ground. Access turns basic upkeep into a marine operation. Crews approach by boat and transfer to the rock only when waves allow. Automation removed the need for a permanent keeper, not the need for people. The light, power equipment, masonry, and metal fittings still require inspection and repair. Salt spray penetrates masonry and attacks metal. Wind loads the tower from every direction, while storms drive water across the lower rock. The first structure was lost during the Second World War. A replica returned to the same pillar in the 1990s, accepting the same narrow footing and exposed approach. Tourlitis remains operational only through weather windows, boat access, inspection, and repair. The lighthouse challenges wind and waves, but the sea still decides when the work can begin. Xiaolangdi releases an artificial flood not simply to move water, but to move the earth carried inside it. At Xiaolangdi, bottom outlets discharge sediment-heavy water at thousands of cubic meters per second, turning stored mud into a fast-moving load. The pressure begins upstream on the Loess Plateau. Storms strip loose soil into the Yellow River in enormous concentrations. That sediment leaves two choices. If it settles behind the dam, flood control storage shrinks. If it settles downstream, the riverbed can rise behind levees. Operators answer with timing. Reservoir levels, incoming water, sediment readings, and downstream conditions determine when the gates open, often before the main flood season. The release forms brown standing waves and powerful currents. One operation can move tens or hundreds of millions of tons through the dam and scour the channel below. Yet mud and sand also wear down the machinery directing them. They grind gates, turbines, concrete, and outlets. At high speed, collapsing bubbles pit surfaces and vibration shakes equipment. Every flush, therefore, creates the next round of inspection and repair. Since regular operations began in the early 2000s, sediment has kept moving and kept arriving. Xiaolangdi can steer sediment, but it cannot erase the river's rule. Erosion upstream becomes pressure somewhere else. A wall can command the Yangtze at one point, yet its pressure spreads across an entire basin. The Three Gorges Dam runs for more than 2 kilometers, rises nearly 200 meters, and holds back tens of billions of cubic meters of water. Its turbines deliver about 23 gigawatts, placing the station among the world's largest. But electricity is only the visible result of a much wider task. Before summer floods, operators lower the reservoir to create storage. Rising water is absorbed, then released through turbines and spillways under controlled conditions. That control shifts pressure rather than removing it. The reservoir reaches hundreds of kilometers upstream, where changing levels affect valley slopes, tributaries, ports, and relocated settlements. On unstable banks, repeated filling and drawdown can influence landslides. Trapped sediment also reduces storage and changes how much material reaches the river below. Flow timing and water temperature change as well, affecting fish movement, habitats, and water quality. Each adjustment solves one demand while creating another downstream. The concrete barrier is only the center of the work. Crews must keep checking seepage, concrete movement, gates, turbines, slopes, and sediment across the reservoir. Three Gorges displays immense human power, but not final control. The Yangtze remains the opponent. Every stored flood and altered bank returns as another engineering demand. This arch does not carry the river's full force alone. It pushes that force sideways into both canyon walls. Baihatan's double curvature arch rises nearly 300 meters and spans about 700, wedged into the narrow Jinsha River Gorge between Sichuan and Yunnan. Its curve does the main work. Reservoir pressure travels through the concrete into abutments on both canyon walls, making the rock part of the dam. That transfer demands deep excavation, rock reinforcement, grouting, and continuous monitoring. Any weakness in a valley wall changes how the whole arch carries water. Powerhouses buried inside both banks hold 16 generating units, each rated at 1 gigawatt. Together, they form one of the world's largest power projects. The concrete also had to be controlled as it hardened. Massive pores generate heat. Low heat materials, cooling systems, and embedded instruments limited cracks inside the arch. Released water brings another test. Outlets and spillways must remove energy before flood flows erode the dam toe or the valley below. Seismic movement, steep slopes, seepage, and reservoir pressure remain after construction. Crews keep reading instruments and checking how concrete and bedrock share the load. The scale has changed, not the bargain. The arch passes water pressure into the mountains, while instruments watch that agreement every day. I do not call these places proof of mastery. The strongest concrete still expands and contracts. Steel still corrodes in salt air. Anchors still depend on rock that can split. Foundations still depend on ground that can move. Engineering earns time by reading those forces early, giving loads a safer path, and inspecting again before small damage spreads. That is the plain lesson. Great structures are not permanent answers. They are maintained agreements with wind, water, ice, rock, and unstable earth. As coastlines shift, glaciers retreat, storms intensify, and rivers carry sediment, those agreements will cost more to uphold. Nations that inspect, adapt, and repair before weakness widens will protect more than landmarks. They will protect transport, energy, trade, and political confidence. In this century, endurance will depend less on building once than on answering nature without pause. Continue with this series as it follows structures under relentless natural pressure across a changing planet, examining the discipline, maintenance, and restraint required to keep them standing for decades.